A military airfield is an extremely vulnerable target. Dozens of expensive aircraft concentrated in a relatively small area are an ideal target for an enemy missile or artillery strike. How does a modern army protect such facilities? The first level of defense is dispersal and cover. Modern air bases build fortified shelters for aircraft, durable concrete hangars that can withstand a direct hit from an artillery shell or shrapnel damage from a nearby rocket explosion. Whenever possible, aircraft are dispersed throughout the base rather than concentrated in one place, reducing the effectiveness of a single strike. The second level is early warning systems. Radars monitoring the airspace around the base can detect an incoming ballistic or cruise missile from afar, giving personnel time to take cover and, if possible, scramble aircraft before impact. The third level is active missile defense. Short-range systems, such as the Patriot system for intercepting ballistic and aerodynamic targets at medium range, or point defense systems such as TSRAM, counter-rocket artillery mortar, specifically designed to intercept unguided rockets, artillery shells and mortar mines at very close range, systems that use rapid-fire automatic cannons to physically destroy incoming ammunition in the air. The fourth level is active interference and deception. False positions or mock-ups of aircraft, inflatable or made of inexpensive materials, placed in places visible to radar and satellite reconnaissance, designed to divert some of the enemy's attacks to empty targets, keeping the real equipment unharmed. The fifth level is the dispersal of the basing concept itself. The already mentioned Agile Combat Employment Doctrine of the U.S. Air Force involves the use of many small, temporary sites instead of several large fixed bases, which significantly complicates the enemy's task of delivering an effective massive strike. It is difficult to destroy aircraft if they are dispersed over dozens of inconspicuous points between which aircraft are constantly moving. Finally, passive protection of personnel, shelters, bunkers, distributed placement of critical base infrastructure so that a single successful strike cannot simultaneously destroy the runway, fuel depots, control center and personnel living quarters. None of these measures alone provides 100% protection. But taken together, dispersal, cover, early warning, active interception and deception, they significantly increase the survivability of an airbase even under the threat of a massive missile attack, which in modern conflicts has become one of the main threats to the air force of any country. F-15, 2 engines. F-16, 1. F-22, 2. F-35, 1. The difference is not accidental. Behind it is a whole philosophy of fighter design where reliability, cost and flight performance collide. Let's start with the obvious argument in favor of 2 engines: redundancy. If one engine fails over the ocean or over enemy territory, the second one allows you to fly to a safe zone. This is critical for carrier-based aviation, where a forced landing on water when a single engine fails means an almost guaranteed loss of the aircraft, and often the pilot. That is why most carrier-based fighters are twin-engine. F-14 Tomcat, F-18 Hornet, both twin-engine. The U.S. Navy fundamentally does not want to risk a single engine above water. But the single-engine design has significant advantages. Less weight: one engine is lighter than the infrastructure for 2. Less fuel consumption at the same thrust. Lower maintenance costs: you need to maintain one set of systems, not 2. Less fuselage volume allocated for the power plant means more space for fuel, equipment, and weapons. The F-16 was originally designed as a light, cheap, maneuverable air superiority fighter, the Pentagon's fighter mafia concept in the 1970s. One powerful Pratt & Whitney FSTO engine provided a thrust-to-weight ratio of more than 1, that is, the plane could literally accelerate vertically upward. Reliability statistics for modern turbojet engines have improved significantly since the 60s and 70s, when a bias formed in favor of 2 engines. The failure rate per flight hour for modern engines is orders of magnitude lower than half a century ago. That is why the Pentagon decided on a single-engine EF-35 even for the deck-based version, which would have been unthinkable in the 60s. Nevertheless, the twin-engine design remains the standard for heavy, long-range air superiority fighters, the EF-15 and EF-22. Not only reliability is important here, but also total thrust. To achieve extreme acceleration and climb rates, one engine is simply physically not enough. The choice between one and two engines is always a choice between cost of ownership and safety margin. There is no universal correct answer, there are only different compromises for different tasks. In an air battle over an area with dozens of aircraft, friendly and foreign, one of the main questions is, how to understand who is who before pressing the missile launch button. A mistake here means a strike against one's own people, what is called friendly fire in military parlance. The system that solves this problem is IFF, identification friend or foe, identification of friend or foe. The operating principle is based on radar request response. A ground station or aircraft with an IFF system sends a coded radio request signal towards the detected target. If the target is its own aircraft, equipped with the appropriate transponder, it automatically responds with a coded signal at a certain frequency. The response contains information, confirmation of ownership, sometimes tail number, altitude, speed. If there is no answer at all, this is an alarming signal, but not final proof of hostility. There could be an equipment failure, there could be a deliberate shutdown of the stealth transponder by one's own aircraft on a reconnaissance mission. That is why the mere lack of response from the IFF is not enough to make a decision to attack. The modern version of the system, Mode 5, works on encrypted, constantly changing codes. This is critical because older versions of the system, Mode 3 and 4, were at risk of being tampered with. If an enemy gained access to equipment or codes through captured vehicles, they could theoretically make their aircraft appear friendly to legacy identification systems. Cryptographically secure Mode 5 codes change on a schedule synchronized among all friendly forces and virtually eliminate the possibility of tampering without access to the actual private encryption keys. But the system is not perfect. Infamous incidents of friendly fire in the history of military aviation, including the tragedies over Iraq in the 90s and 2000, often occurred not because of the failure of IFF technology as such, but because of the human factor, incorrect interpretation of data, the stress of the combat situation, temporary technical difficulties when working in a coalition with different types of equipment from the Allies. That is why modern doctrine requires a combination of several sources of confirmation, not only the IFF signal, but also visual contact where possible, data from AWACS, coordination through voice communications with air combat controllers. Technology reduces risk. But the final decision always remains with the person, who must bring together several sources of incomplete and sometimes contradictory information in a matter of seconds. Before a military jet engine can be used on a combat aircraft, it undergoes testing that is comparable in duration and cost to the development of the aircraft itself. Why does this take years, and what exactly is being tested for so long? The first is resource testing. The engine is installed on a special test bench and runs for thousands of hours in a row, simulating the full life cycle of operation, takeoff modes, cruising flight, afterburner, landing modes, and so on in a circle. Engineers monitor the slightest signs of metal fatigue, microcracks, and wear of turbine blades. Particular attention is paid to thermal cycling, repeated cycles of heating and cooling. Each takeoff with afterburner heats the turbine to temperatures above 1,300 degrees Celsius. Each landing and engine shutdown causes cooling. Metal expands and contracts thousands of times over the life cycle of an engine, and it is these cycles, not absolute temperature itself, that most often cause fatigue failure. The second is foreign object ingestion tests. A special cannon shoots chicken carcasses into a running engine, simulating a collision with birds at different speeds and altitudes. This is not a joke or an exaggeration. A collision with a bird at takeoff speed can damage the engine, and on military airfields, especially near the coasts, birds are a real and frequent threat. The engine is also tested for ingestion of ice, sand, and even small foreign metal objects to understand under what conditions the compressor and turbine remain operational, and under what conditions a catastrophic failure occurs. Third, testing in extreme temperatures. The engine must start and operate equally reliably at -40 degrees at Arctic bases and at +50 in the desert conditions of the Middle East. Each such temperature regime requires a separate test cycle, because the viscosity of the oil, the behavior of the seals, the thermal clearances between parts, all this changes depending on the temperature. Fourth, tests at high altitude stands, simulating the rarefied air of high altitudes, where there is less oxygen for combustion, and cooling conditions are completely different than at sea level. The total duration of the full cycle of qualification tests of a new military aircraft engine is from 5 to 10 years. And even after being put into service, the engine continues to be monitored throughout its entire operation. Every flight hour is recorded, the data is analyzed, and if deviations are detected, directives are issued for additional checks of the entire fleet. The engine is the heaviest and most critical component of a combat aircraft. That is why his tests spare no time or money. A fighter departing from an aircraft carrier or remote base has a limited supply of fuel and ammunition. In a protracted campaign, such as in Afghanistan, aircraft cannot constantly return to the main base thousands of kilometers away. This is where the Forward Arming and Refueling Point concept, or FARP for short, comes into play. It's a temporary, often minimalist area, sometimes just a cleared patch of land or a short runway, where helicopters and some types of airplanes can land, refuel, resupply, and take off again in a matter of minutes. This concept is especially actively used for attack helicopters such as the Apache. In a combat operation, a helicopter can work on a target, expending missiles and shells for a cannon, and instead of a long flight to the main base, land at a nearby FARP, refuel and rearm in 15 to 20 minutes, and then return to the combat zone. Logistically, this is an extremely difficult task. Fuel and ammunition must be delivered to such a site in advance, often by supply helicopters or heavy transport aircraft S-133, capable of landing on unpaved strips. FARP personnel are a specially trained small team that operate in high-risk environments, often in close proximity to a combat zone, with no capital fortifications and minimal protection. The speed of the operation is critical for two reasons. Firstly, tactical, the faster the helicopter returns to battle, the more effective the support of ground troops. Secondly, the safety of the site itself, the accumulation of fuel, ammunition, and stationary helicopters on the ground is an extremely attractive target for the enemy, and minimizing the time equipment spends on the ground reduces this risk. Modern armies are developing the concept of dispersed operations, agile combat employment in the terminology of the U.S. Air Force, where, instead of several large, well-protected, but easily detectable bases, many small, temporary, hard-to-detect sites are used, between which aircraft and personnel constantly move. This greatly complicates the enemy's task of launching a massive strike on the aviation infrastructure. If there are hundreds of bases and they are constantly changing, it becomes almost impossible to destroy aviation with one strike. FARP is an invisible but vital part of modern air warfare. The rear, moved as close as possible to the front. Many combat trainers and some combat aircraft have two cockpits located one behind the other, each with a full set of controls. Why duplicate controls on a combat aircraft, increasing its weight, cost, and reducing flight characteristics? The first and main reason is pilot training. Before a student takes the controls of a supersonic fighter aircraft solo for the first time, he must log dozens, often hundreds of hours of flight time under the supervision of an experienced instructor who sits in a second cockpit with full redundant controls. The instructor can take control at any time if the cadet makes a dangerous mistake. Combat trainers such as the T-38 Talon or the more modern T-7 Red Hawk are specifically designed for this purpose. The instructor's rear cockpit is located slightly higher than the front one to provide good visibility and control over the trainee's actions. The second reason is tactical specialization in two-seat combat vehicles. For example, the F-15I Strike Eagle or the F-18F Super Hornet in the two-seat version is the rear crew member, the weapon operator, responsible for managing complex aiming systems, working with precision weapons, coordinating with ground forces, freeing the pilot from part of the cognitive load and allowing him to focus on piloting and general situational awareness. In complex strike missions, especially at night, in bad weather, when working with several types of weapons simultaneously, the distribution of tasks between two crew members significantly improves the efficiency and safety of the mission compared to a single-seat option. The third reason is the specificity of some types of aircraft, such as electronic warfare or reconnaissance aircraft, where the second and even third crew member controls specialized equipment that requires constant attention and is not directly related to piloting. But the two-seat design also has obvious disadvantages for purely combat fighters. The additional weight of the second cabin, ejection seat, and life support systems is several hundred kilograms that carry neither weapons nor fuel. Additional air resistance from the enlarged fuselage reduces maneuverability and speed. That is why most modern pure air superiority fighters, such as the EF-22, exist exclusively in a single-seat version. The priority here is maximum flight performance, not distribution of workload among crew members. The choice between one and two crew members is another classic military aviation trade-off, where gaining one almost always means losing the other. A missile is fired at your aircraft from the ground or from another aircraft. You have just seconds to react. How does a modern fighter jet know that it has just been shot at? The first line of detection is Radar Exposure Warning, RWR system, Radar Warning Receiver. Special antennas located around the perimeter of the aircraft constantly scan the airwaves for radar signals directed at the aircraft. The system analyzes the nature of the signal, its frequency, scanning mode, intensity, and determines not just the fact of exposure, but also the type of radar that created it, and often the specific type of threat that this radar serves. Particularly important is the difference between the usual search radar scanning, when the beam simply passes through the aircraft as part of a general overview of space, and the target tracking mode, when the radar is fixed on your aircraft and is preparing to issue target designation for launching a missile. The RWR system provides the pilot with an audible and visual signal of varying intensity depending on the severity of the threat, ranging from a simple warning to an immediate launch alert. The second line is detecting the very fact of a missile launch. Modern missile warning systems, MWS, missile warning system, use a combination of sensors. Ultraviolet sensors record a characteristic flash from a rocket engine at the moment of launch. It differs from the background radiation of the environment by a specific spectrum that is difficult to confuse with anything else in nature. Infrared sensors track the further flight of the rocket along its jet trail. Radar sensors warning of the approach of a missile operate in the final stage. They directly detect an approaching object by its reflected signal and calculate the time until the expected hit. Once a threat is detected, the system initiates countermeasures automatically or at the command of the pilot. These could be heat decoys fired by infrared-guided missiles, chaffs, thin strips of metallized material that create false radar targets for radar-guided missiles, or active electronic countermeasures that interfere directly with the homing head of an attacking missile. Some modern systems are capable of automatically performing an evasive maneuver without pilot intervention at the most critical moment, when human reaction time may be too long. This is a controversial decision from a doctrinal point of view. How much is it permissible to allow a computer to take control of an aircraft in a combat situation? But from a physics point of view, sometimes the count comes down to tenths of a second, where the human reaction objectively loses to the automation. This entire chain of detection and response must be completed in seconds, sometimes even faster. The difference between survival and death in modern air combat is often measured not by tactical skill, but by the speed of electronics. Take a look at the wings and fuselage of a fighter jet. You will see many attachment points to which missiles, bombs, fuel tanks, and containers with special equipment are suspended. Their number and location are far from an accident, but the result of complex calculations balancing firepower, aerodynamics, and stealth. Every suspension point is a compromise. On the one hand, more points means more weapons, more flexibility in choosing the type of ammunition for a specific mission. On the other hand, each external suspension creates aerodynamic drag, reduces the speed and flight range, and also, which is critical for modern fighters, significantly increases the radar signature of the aircraft. That is why stealth aircraft, such as the EF-22 and EF-35, have a fundamentally different concept: internal weapon bays. Instead of hanging missiles externally on pylons, where they create bright radar reflections, the aircraft carries the main ammunition inside special compartments in the fuselage, completely closed from external radar by streamlined doors. This radically reduces the radar signature, but at the same time sharply limits the number of weapons that can be carried. The F-22 carries only 6 air-to-air missiles in its internal compartments, significantly less than older fourth-generation fighters could carry externally. This is why the concept of a stealth configuration versus maximum load configuration exists. In missions where stealth is critical, for example, during the first breakthrough of a dense enemy air defense system, the aircraft flies with a purely internal load, sacrificing the number of weapons for the sake of stealth. In missions where air superiority has already been achieved and the threat of radar detection is less critical, the same EF-35 can additionally hang weapons on external points, significantly increasing the combat load, but at the same time losing most of the stealth advantage. The location of the hardpoints is also carefully thought out from the point of view of balancing the aircraft. Symmetrical mass distribution is critical for stability and controllability, and asymmetrical suspension, for example, when one missile is lost in combat and not another, can create a noticeable roll that the pilot has to compensate manually or through the automatic control system. The number and placement of hardpoints is a frozen-in-metal solution to a whole set of trade-offs between firepower, stealth, and performance that engineers fine-tune throughout the aircraft design process. Before a new missile, bomb, or weapons system gets onto a real combat aircraft and is used in a real conflict, it goes through a long and maximally closed test path from prying eyes at specialized testing grounds. One of the most famous such places is Edwards Air Force Base in the California desert, as well as Nellis Air Force Base in Nevada, where the famous Red Flag Test Site and Training Center is located. Testing of new weapons takes place in several strictly sequential stages. The first is bench testing, where individual components of the system are tested in laboratory conditions, without a real flight. Electronics, fuses, and guidance systems are tested for reliability, resistance to vibration, electromagnetic interference, and extreme temperatures. The second stage is captive carry, captive flight. The missile or bomb is physically suspended from the aircraft and flies, but is not separated from the carrier. This allows you to check how real flight conditions, vibration, overloads, aerodynamic flows affect the operation of the product's electronics, without risking expensive ammunition. The third stage is actual launches against targets at the training ground. Here, for the first time, the full cycle of weapon operation is tested, from separation from the carrier to hitting the target. Targets range from simple towed structures to complex, highly realistic simulations of real enemy military equipment, sometimes even using decommissioned military equipment as real targets. The fourth stage is testing in conditions as close as possible to combat ones, with the use of electronic countermeasures, simulating a dense air defense system, working as part of a group of aircraft, rather than a single carrier. It is at this training ground that the most realistic scenarios for the use of weapons are tested, including conditions of strong interference, adverse weather, and nighttime. Each stage generates a huge amount of data that is carefully analyzed by engineers and military specialists. Any deviation from the calculated characteristics and undershoot, a miss, an electronics failure becomes the subject of a detailed investigation and, if necessary, modification of the design, followed by a repeat test cycle. The full test cycle of a new aircraft weapon, from concept to adoption, usually takes from 5 to 15 years, depending on the complexity of the system. It is long, expensive, and requires a lot of patience. But the alternative, sending untested weapons to war, risks failure at a time when lives are at stake. Logic dictates that a military aircraft should be as fast as possible. Reached the target faster, got away from danger faster, caught up with the enemy faster. But there is a whole class of military aircraft for which low speed is not a disadvantage, but a deliberate and critical design feature. Take, for example, a close air support aircraft, such as the already mentioned A-10, or attack helicopters. Their task is not to catch up with an enemy fighter in aerial combat, but to accurately and effectively hit a ground target, often located in close proximity to their own troops. This requires time to visually identify the target, time to aim, time to distinguish friend from foe on the ground in the chaos of modern combat. At a speed of 1,000 kilometers per hour, the pilot has a split second to make a decision while flying over a war zone. At a speed of 500 to 700 kilometers per hour, the time to analyze the situation increases significantly. In addition, low speed means better maneuverability at low altitudes and the ability to make tighter turns to re-enter a target while remaining within a relatively small combat area. Reconnaissance and patrol aircraft are another example of deliberately low speed. An anti-submarine warfare aircraft, such as the P-8 Poseidon, or the already mentioned RS-135 reconnaissance aircraft, are designed for long patrols at economical speed, and not for rapid movement. Their task is to spend hours in a certain area, listening, observing, analyzing. Here, range and flight duration are more important than speed. There is also a more subtle aspect, refueling in the air and coordination with slower types of equipment. The tanker must fly at a speed that is comfortable for the aircraft being refueled, which often means a significantly lower speed than the maximum possible for the tanker itself. Finally, surveillance drones like the MQ-9 Reaper intentionally fly slowly and economically because their job is to hover over a single point for hours tracking a target, rather than move quickly from one point to another. Their speed is comparable to the speed of a small piston aircraft of the last century, but their effectiveness is determined not by speed, but by flight duration and quality of observation. Speed in military aviation is a resource that is spent for a specific task. Sometimes a task requires maximum speed, and sometimes just the opposite. Fifth part. 50 blocks in total. We looked at something that rarely makes headlines, not the planes themselves, but the logic of the decisions that lie behind every rivet, every system, every compromise. Military aviation is not a collection of impressive machines. This is the result of a continuous dialogue between what you want to get and what physics, budget, and human capabilities allow. And this dialogue continues right now, in closed design bureaus and test sites, the results of which we will see only in years to come.